This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. What's up, you math maniacs? Welcome to section 4.7, day 1, theorems about zeros and polynomial functions. And you know what they say about the fundamental theorem of algebra? You can't really spell fundamental theorem of algebra without fun. And that's what we're going to do today. We're going to have a ton of fun. So, as a side note, actually there's a fundamental theorem of algebra, there's a fundamental theorem of calculus, there's a fundamental theorem of geometry, there's a fundamental theorem of statistics. Someone just decided that there were going to be a whole bunch of fundamental theorems, and basically we're just saying that this theorem right here, this theorem is kind of like the goal for lots of other theorems. Like once you have proven this theorem, you can prove lots of other theorems too. It's kind of like the central core concept idea. It says every polynomial function of degree n, so like if n is 3, then that's what we're calling like a cubic function, where with n is greater than or equal to 1, has at least one zero in the set of complex numbers. A corollary of that, now just to explain that and its significance, this is a side note, or as a result of that, you can say that every polynomial function of degree n with n greater than or equal to 1, remember if n is 2, it's a quadratic function, it can be factored into n linear factors, which are not necessarily unique, like you could have multiplicities going on here. Basically saying that you can take every polynomial function and turn it into this format: a number out front if you want, and then, or if you need, and then x minus a 0 times x minus a 0 times x minus a 0, and there are going to be n of these. Like if it's a cubic function, then n is 3, then there will be going to be 3 of these. Now these are not necessarily going to be unique, but you can always do that. And it's going to be over the complex numbers, so sometimes you might need imaginary numbers, but you can always turn every polynomial into and if you know the degree of that polynomial, like if the degree is 5, if it started off with f of x to the 5th, then you would have 5 of these sets of parentheses, and maybe you might have a number out in front. You can always turn polynomial functions into that format. You can always factor them. So if you wanted to reword the fundamental theorem of algebra, is that you can basically always factor polynomial functions into these factors. And how many of them are there going to be? There's going to be the degree of those. So if you have find a polynomial function of degree 3, then you should have 3 sets of parentheses. It says find a polynomial function, meaning that there are multiple answers. But basically, if the zeros are going to be 1, 3i, and negative 3i, then you plug them in right here. 1, 3i, and then negative 3i because it's x minus that, so you get x plus 3i. Foiling this, you get x squared plus 1, and then multiplying here, x minus 1 times x squared plus 9. I'm going to use the table box method right here. X squared plus 9, x minus 1. So x squared times x is x cubed, 9 times x is 9x, 9 times negative 1 is negative 9, and x squared times minus 1 is minus x squared. There are no like terms to combine, so you're just going to write them all out like this: x cubed minus x squared plus 9x minus 9. Here is the polynomial function. Here is the factored form, and we can see that it has these factors, these zeros, and this is the polynomial version. It has degree 3, and it says a polynomial function. Another polynomial function, you can multiply all of this, like at the very beginning, you could put a number out in front, like 5. Choose whatever number you want, multiply, and that function would also have a degree of 3 and a zeros of 5. You just have like 5x cubed minus 5x squared plus 45x minus 45. That's another version of the answer, but this is the simplest version. Example number 2. Find a polynomial function of degree 5 with negative 1 as a 0 of multiplicity 3, 4 as a 0 of multiplicity 1, and 0 as a 0 of multiplicity 1. So there it is. Negative 1 is this factor with a multiplicity of 3. 4 as a multiplicity of 1, there's an unwritten 1 right here, and 0 as a multiplicity of 1, there's an unwritten exponent of 1 right here also. So this is it. You set up the function. This is the factored form, but we want the polynomial function. So we have to basically multiply it all out. X plus 1 cubed is using the formula that we had memorized from chapter 1, was it? Yeah, chapter 1. This becomes x cubed. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And there it is. And then we have this right here. I'm going to multiply this green part and this blue part right here, green and blue. And instead of, you could use the table as I used before in the first problem, but I'm going to use kind of like the multiplication version right here. This is kind of like 4-digit and 2-digit multiplication. You know, you've got the rows, you do multiply 4 times all of these terms here, or minus 4 times all of these terms, and then multiply x times all of these terms, and right here, make sure you insert the 0, and then if they are all lined up the right way, then the like terms are going to appear above each other, and you can just add to get your answer right here. Again, this is something we did in chapter 1. It's been a while since we've seen it, but that's what it looks like. And so this gray part is what you get when you multiply the green times the blue. Then the last part is to distribute the x, and so x to the 4th becomes x to the 5th, and all these terms appear. This is the answer. It's a polynomial function of degree 5 with all of these zeros with the right multiplicities. Here's another theorem. Remember, these are theorems about zeros and polynomials. Here's another theorem. The non-real zeros. You can read all the details if you want, but basically the idea is that non-real zeros occur in conjugate pairs. Non-real zeros occur in conjugate pairs. Here is here's an equation, and it's equal to 0. One of the zeros, one of the solutions of this, would be 1 plus I. So therefore, the other solution has got to be 1 minus I. This is a non-real zero, and it occurs in a conjugate pair. So these two are conjugates. If one of them, then you can say that you can predict what the other one would be just by knowing its conjugate. Similarly, you can say that irrational zeros occur in conjugate pairs too. Like this. Example 3, find the other zeros of a polynomial function of degree 6 with rational coefficients if 3 of its zeros are given like this. So if we're just given rational coefficients, like if we're not allowed to have as the function a complex coefficient, then the zeros are going to look like this. You've got conjugate, conjugate, conjugate. 3 of them are given, so therefore the other 3 can be known just by knowing what their conjugates are. Conjugates, again, just change the sign of the, if it's plus, you change it to minus. If it's minus, you change it to plus of the second term. Find a polynomial function of lowest degree with rational coefficients that has a negative square root of 3 and 1 plus I as 2 of its zeros. Well, the other 2 zeros have got to be square root of 3 here and 1 minus I here. The lowest degree is going to be a degree of 4 because we've got 4 different zeros. 1, 2, 3, 4. If you're going to, in order to make sure that you have rational coefficients. So we're going to take these 4 zeros and turn it into a polynomial function. These 2 zeros get turned into this, and the other 2 zeros get turned into this, x minus all the zeros. I'm going to FOIL these. Remember that it's the difference of squares, so you get x squared minus 3. And then here, I'm going to take an additional step to save a lot of calculations. You could, if you wanted to, make a 3x3 table, and you could FOIL all of this out. One thing I'm going to do is I'm going to take a cube from over here, and I'm going to arrange it into the difference of squares. So the plus, a, this was a minus b times a plus b. I'm going to arrange it to be the same way here. A minus b times a plus b. I did that by kind of just grouping these together. So this is going to be a squared minus b squared. And if you do that, then the I turns into a negative 1, so minus I squared is plus 1. You have to FOIL this out. You get x squared minus 2x plus positive 1. And then you can even combine the 1s to get 2. So we have x squared minus 2x plus 2 all times x squared minus 3. I'll use the table method over here. You can see that's the blue part times the green part. Blue part times the green part is here. X squared times x squared is x to the 4th. Negative 2x times 2x cubed. 2 times x squared is 2x squared. Here, you're going to x squared times negative 3 is negative 3x squared. Negative 2x times negative 3 is positive 6x. 2 times negative 3 is negative 6. The only like terms to combine are the quadratic terms. All the other terms have different degrees. But the quadratic terms, negative 3 plus 2 is negative 1. And that's why there's only negative 1 right here. So the answer is going to be x to the 4th minus 2x cubed minus x squared plus 6x plus what? Look at the table and try and figure out what I've blotted out right here. And just like General Grant did when he was winning the Civil War and he became president, Ulysses S. Grant is your audio check guy, and I want you to figure out what I've blotted out, what number. I want you to start the assignment 4G1, copy the problem list, do the first problem, and I'll see you in class.